All right. I'd like to thank the organizers for organizing this conference and the extenuating circumstances that we're meeting here. Appreciate anybody watching this video. I'm going to talk about my work with Brianna Sorenson and John Sorenson on an algorithm and estimates for the Erdős-Selfridge function. We're all at Butler University. Brianna Sorenson just graduated and will be attending the University of Wisconsin at Madison in the computer science program. So thank you for your time. So the Erdős-Selfridge function is the function that measures the g of k choose k, and we want that binomial coefficient to avoid divisibility by small primes. And what we mean by small primes is any prime less than or equal to k. And Paul Erdős posed this problem in 1969. That's why it's of some interest to us. It's also in the online encyclopedia of integer sequences. And so there's been some previous computational and theoretical work on this. So we can go over a few simple examples. The binomial coefficients are most commonly known with Pascal's triangle, and you can kind of just see some of the small examples. We can look at g of 1. 3 choose 1 is 3, and so the least prime factor of 3 is greater than 1, so that's easy to see. G of 2 is 6, since 6 choose 2 is 15, and 15's least prime factor is greater than 2. G of 3 is 7, since 7 choose 3 is 35, the least prime factor of 35 is 5, which is greater than 3. And similarly with G of 4, it is also 7, since 35 is its least prime factor is greater than 4. And you can keep going in this manner. This is not, using Pascal's triangle is not a very computationally efficient way of finding these though. So in 1974, Eklund, Erdős, and Selfridge did the first small tabulation of these values, computing the first 40 and some sporadic values above there, where they determined that g of k was larger than some bound, which is 2.5 million, or they found g of k. And we kind of see some of the chaotic behavior that g of k exhibits. It kind of jumps around. But we suspect it grows like e to the k over log k. The next major computation was due to Scheidler and Williams in 1992. They used a sieve algorithm with congruences coming from Kummer's theorem, and they computed g of k for up to k equals 140. You can see this table. There's a minor typo there, but you know, if you want to look at the numbers carefully, you'll see the previous work is verified, and they got some more. They had access to customized special purpose sieving hardware, and they revisited the problem a few years later, and were able to compute k less than or equal to 200. And the same basic idea is they used Kummer's theorem, which I'll explain in a second. I'll show in a second. To construct efficient sieving problems. So again, the chaotic behavior of g of k seems to remain, and that's what we expect to kind of jump around but still grow and grow quickly. Kummer's theorem gives a nice criteria for when n choose k is divisible or not divisible by a prime. So if we write k and n in their base p representation, it's to say the coefficients in n and the representation of n need to be greater or equal to the coefficients in the representation of k. And so we can use this theorem to construct to write down congruences for every prime power less than or equal to k that we know g of k must satisfy. And so here's an example. It'll be a running example with k equals 10. If k equals 10, and we want to look at n. We want to know if 12 choose 10 is divisible by 5. Coomer's theorem says in base 5 representation, 10 looks like 2, 0, and n looks like 2, 2. And so 5 does not divide 12 choose 10. What about 3? Well, the base 3 representation of 10 is 1, 0, 1, and the base 3 representation of 12 is 1, 1, 0, and now 3 does divide because we have this 1 greater than or equal to 0. And so our idea is we can look through all the prime powers, prime power moduli. If we combine them all together, we can search through them all and find and list all possible acceptable residues. And we just need to find the correct one. In fact, it would be the smallest one, subject to a very minor constraint that it is greater than or equal to k plus 1. Continue our example. What does this mean for k equals 10? Well, for the prime 2, we need to look modulo 16, and we write down the 10 in base 2, and then we write down every base 2 expansion that Coomer's theorem says would qualify. So if k is 1, 0, 1, 0, here are the 4 valid base 2 representations of n mod 16. Similarly, we do this for 3. K is 1, 0, 1, and so we can write down the 12 base 3 representations of n mod 27. P is 5, so K is 2, 0. We can write down the 15 acceptable congruences mod 25, and similarly with 7. And so in the end, we have this list of 4 times 12 times 15 times 24, 17,280 residues, one of which will be G of K. But we know this is too many residues. And so we have an estimate that we'll explain a little later, but we believe that G of 10 should be less than 306. So we look for a modulus, a divisor of m sub 10 that is just larger than 306. It turns out 2 to the 4th times 3 times 7 satisfies that. And the number of residues that satisfy, that are admissible modulo this 336 is only 32. And we know that G of K must be among this set. So if we search through these 32 residues, we'll be able to find G of K. So to kind of compare this to the previous work by Scheidler and Williams and Lukes, it's as if we said that they had their residue set that they started to sieve by, we're just going to make that residue set large enough that the starting residues, that the starting set of residues, that G of K will be in there. That's another way to think about our work. So to construct these residues, we'll use a wheel data structure to do this efficiently. And I'll explain how we picked 336. We used it's a knapsack problem. I'm not going to spend a lot of time going into this, but basically we just need to rank how powerful a given prime power modulus is based off of the number of admissible residues. And so we want to minimize the number of residues while constructing a big enough modulus that G of K will be in there. So once we have our way of evaluating a given prime power, our approach is really simple. It's just use the greedy algorithm. And it seemed to work well, but this is a knapsack problem, and we know that in theory it can be very difficult to solve optimally, but the greedy algorithms seem to work. And so here we kind of see for our small running example, we see the filter rates of 2 to the 4th, 3 to the first, 7 to the first. They have a very pretty good filter rate, and this is why we rejected these other ones. They don't have as good a filter rate. So 3 cubed, 5 squared, so forth and so on. All right, and of course, one thing that kind of differs is it's not just a matter of choosing a prime power. You can choose the exponent. So you want to choose kind of for the small primes, you want to choose the optimal prime power for that. You might not choose all the high. You might not choose the highest power of 2, for example. You might only choose half the exponent. Depends on the base P representation. So here's some, for a larger example, more robust, you can see that for large primes, almost always the exponent will be 1 that you would want to consider. For the small primes, you might consider higher powers. You can see the 2 to the 5th and the 7 cubed. And you see this data. Anyway, so here's our wheel data structure. Let me go back really quickly so you can see, kind of remind you where these numbers come from. So if recall, there are 4 admissible residues mod 16. It turns out we're only using the not the full power of 3. So we're not using mod 27. We're using mod 3. So just this, it's as if we're only going to look at this 1 here. We're ignoring 5, and we're going to pay attention to the fact that the constant place with respect to this, the base 7 representation is 3, and that's what we see here. Is there are 4 admissible residues mod 16. There's 2 admissible residues mod 3, and there's 4 admissible residues mod 7. And how this table works is that once you know what congruence class your number is in, the jump tells you the nearest entry in the table and the minimum number you add to it to get to the next admissible number. So if you're 0 mod 16, you add 10 to 16 to get to 10 mod 16. It's fairly straightforward. Then at the next layer, in order to preserve the congruence mod 16, but to find the next admissible congruence modulo 3, you just need to compute the appropriate multiple of 16 to add. Likewise, the next layer of the wheel is the congruence is mod 7. So now at this layer, you're thinking we have set some residue mod 16 and mod 3. So to preserve that, this layer, you need to add the correct multiples of 48 to not destroy the congruence information mod 3 and mod 16. And so the jumps are listing the minimal multiple of 48, 3 times 16, to get to the next admissible residue mod 7. So let's see how this works. And you would construct another set of wheels. I'm not going to show those for the filters because you still need to consider the higher powers of 3, the higher power of 7, and the powers modulo 5 for admissibility to see if it works. So I'll explain this. Now, so how do you start? Well, we know that G of 10 has to be at least 12. So we start at 12, but go back really quickly. 12 here on this table is not admissible, so we have to add 2 to get to the next admissible term. So once we go to 14, 14 is now admissible mod 16. So we step down and we check, is 14 admissible mod 3? 14 mod 3 is 2. 2 is admissible, so we don't really have anything to do. So we step down and check if 14 is admissible mod 7. It's not, so we have to add something. And so then we add 48. And then so we get our first candidate that we have to filter. So we check 62. 62 is 62 fails mod 27. So it is not a candidate for G of K. We stay on that bottom level of the wheel, and the next element is generated by adding 48. So you add 48 to get 110. We check if 110 is a candidate for G of K. It also fails the mod 27, so forth and so on. So finally, we get to 206. We're at the last level of the mod 7 wheel. We layer, ring, we step back up to the mod 3. So we're at 14. We add 32 to get 46. We check, is 46 admissible mod 7? It is. So now we check, does 46 pass our filters? And it does. G of 6, 46 passes all the filters. And so at this point, all we know is that G of 10 is less than or equal to 46. Now, it turns out G of 10 is 46, so in a certain sense, we know we're done. But let's talk about what the algorithm continues to do. These next 3 elements aren't going to be generated because they're too large. So we're going to step back up here. You kind of see this. Go to the, oh, actually, we step all the way back up. We're done with the 3 rings, so we step all the way back up, add 1, go to 15, 15 to 30, 15 gets stepped to 31 in the 3 ring, 31 is admissible, 31 is less than 46, so we need to check it in the filters, it will fail. And so everything from here on out will continue this process, and there's only 2 outcomes that can happen. Either it fails a filter and it's less than 46, or it's greater than 46 and we don't bother generating it. So under the assumption of a uniform distribution heuristic, we think this out. We prove our algorithm is sublinear in G of K, and we think we can prove it sublinear without this assumption once we kind of can count enough primes. I'm not going to go into the details of this. That's a little beyond the scope of this talk. I would love to answer questions in the more technical session. But I want to sketch some of the work that we did. Basically, the idea is in our example is we said, let's choose a modulus greater than 306. And so we said, well, let's look at the total residue, the total size of the modulus that all prime powers contribute, and let's look at the number of residues. And if we divide that, if we look at that quotient, we would expect G of K to be roughly around this point. Scheidler, Williams, and Lukes kind of realized the significance of this number in their previous work. And so if these residues, these RK residues are kind of uniformly distributed, then this is a very reasonable size to look at. And so we choose this G hat times K as our upper bound, so that probabilistically our algorithm, we're choosing a modulus that we feel very confident will have G of K among the residues generated. And here you can see some of the data we gathered up to about 353 in this chart. And except for this little outlier here, but computationally being below is fine. All of the G of K values are within the expected error that we wanted. Here's kind of zoomed in. Here's where we think it is e to the k over log k, right there, the blue line, but this is more data. If you want to look at the proof, I'll just kind of talk about it in a big picture way. There's 3 key portions of the proof. Basically, you need to look at the base P representation. You need to look at the modulus, and so you look at this quotient. We break this quotient up into 3 portions. The part of the quotient that comes from the small primes and the coefficients associated with their representations, the larger primes, and then we further break this product up into the coefficients on the linear term of the base P representation, and the linear term and the coefficients on the constant term of the base P representation. And it turns out that the main difficulty is the blue product. And so a good chunk of our proof deals with how to analyze the product in blue there. And so I'm not going to spend too long. You can pause the video if you'd like, but here's a bunch of G of K values we computed. We did these all with a single core. And it didn't take too long, but eventually we needed to parallelize this computation, and we did that. And so we've been running on 192 cores. We have about 16 more values that aren't on this, this screen. But anyway, you can scan these if you'd like. This happened 5 times, so I'm going to conjecture it happens infinitely often. So here's more G of K with the higher values. Again, we still see G of K behaves very chaotically. Similar. So to summarize, we have an algorithm to compute G of K that is sublinear. We've computed up to 300 G of 377. We believe that our approximating function is a very good approximation of G of K. Brianna, for her senior thesis, explored other ways to deal with the knapsack problem to see if she could find ways to beat the greedy algorithm that were not too computationally inefficient. And so if you have questions about that, we'd be happy to answer them. That's the talk. I look forward to answering any questions in the more technical session. I hope you enjoyed it. Thank you for your time.